bin Syarif Fairuz. I'm from Group 19. To begin, let us look our core research focus. We set our answer a fundamental question: how amplitude variation across different microphone sensor smartphone model. And for my research objective, first, to see if different microphone sensor smartphone models record different amplitude when they record to the same sound at the exact same time. To find out if this second objective, to find out if this amplitude different are caused by each smartphone microphone sensor part. For my dependent variable, measure amplitude for the same sound source and geometry. For independent variable, microphone sensor for different smartphone model. For my hypothesis, if the same sound source is measured simultaneously by different microphone sensor smartphone model, then the record declarable levels will vary significantly across the device because individual hardware different in microphone sensitivity and software-driven adjustment like automatic gain control create a unique calibration profile for each type of microphone sensor smartphone model. For my equipment, and then moving on to our experimental setup, which you can see the illustrated slide. To maintain structural integrity, I strictly control our geometry. I use a laptop for our fixed sound source, playing our Group 19 audio sample in the uncompressed. I test two distinct smartphone hardware architecture placed an exact distance for 30 cm and from the laptop speaker and spread by spacing of 50 cm. The first design was an iPhone featuring a standard MEMS microphone. The second was a Android device which utilized a dual blackpad MEMS microphone. A physical ruler was deployed to guarantee that both sensors remain precisely aligned with the acoustic field, ensuring the receive the exact same sound pressure simultaneously. And then for my procedure, first, for control condition, to ensure the recorded sound is accurate with minimal environmental interference or outward frequency distribution. For safety precaution, to protect your hearing, minimize the exposure to high volume audio source during consecutive recording session. Restrict exposure duration to mitigate physical discomfort. For recording procedure, first, use as fixed sound source and fixed distance, and then second, place the laptop and the smartphone at the fixed distance. Third, ensuring no sound at surrounding. Fourth, play the audio on the lap and record it with the smartphone for data 1. Fifth, convert the recorded audios M4A to WAV. And lastly, insert the convert audio into the side lab with code save and execute the wave. And then for now, let's talk about the how I process this raw data using Skylab instead of blindly grabbing random segment of the audio file. Our script was engineered to be highly demand-urban. First, clear figure window and load audio file. Second, I use code to the convert stereo to mono, and then find the loudest point. And fourth, define a slash window around the loudest part with safety check. And then I extract the real wave slide and boot the time axis. And then I do the subplot 1 waveform granted to have data. And then Fourier transform calculation, and then lastly subplot 2 frequency spectrum. So next, I want to explain about the result data and the waveform analysis. Let us look the visual result generated by Skylab script. Here we can clearly observe the distinct waveform and frequency response between the two devices. When I break down the quantitative values in our waveform analysis table, the data reveal stark contrast. The iPhone MEMS microphone capture a complex waveform with sharp peaks reaching a peak amplitude of the approximately 0.39. Conversely, the Android dual blackpad MEMS microphone display a significantly dampened response, capturing a peak amplitude of only about 0.21. Looking closely at the frequency spectrum graph, both devices capture the harmonic spike of the 600 Hz square wave, However, the vertical amplitude scaling across this frequency is vastly different. The small wave on the iPhone is incredibly consistent, where the Android show is heavily modified suppressed envelope. And next, for my discussion, hypothesis relation. The experiment result fully support the original hypothesis. A smartphone specific hardware and software significantly alter how it measures sound volume. Even when exposed to the exact same sound, the two devices produce completely different digital measurement for the three main reasons. For first reason, different hardware component. The iPhone used a standard microphone, while the Android use a modified design dual backplate MEMS. Because they handle sound pressure differently, the Android record a much lower peak volume 0.21 compared to the iPhone 0.39. Software audio adjustment. Both phones use a built-in software to process sound. The Android system AGC appearing to the aggressively reduce the volume to prevent the audio from distorting. And third reason, unique frequency sensitivity. Each microphone naturally capture certain pitch, stronger or weaker than the other. And for discussion, next discussion, error and limitation. The accuracy of the experiment may have been affected by a few key limitations. Because consumer smartphone use a boot audio software that cannot be turned off, it was impossible to capture purely raw sound data. And then finally, converting the audio file from FOA to WAV for analysis might have introduced minor digital errors or subtly alter the precise volume measurement. For implication, this finding show that everyday smartphones are not reliable for precise sound measurement unless they are individually calibrated. This limitation is highly important for app developer, audio engineer, and forensic expert who rely on the accurate audio data. Because different phones use unique microphone hardware and automatic software adjustment, their recording cannot be simply treated equally or directly compared. So for conclusion, the experiment fully support the hypothesis. Measuring the exact same sound with the different smartphone result in significantly different volume reading. For instance, the iPhone recorded a peak amplitude of 0.39 while the Android record only 0.21. This variation happened because each device relies on uniquely designed physical microphone and the proprietary software to automatically adjust the audio. Ultimately, this proof that everyday smartphone cannot be used as a standardized sound measurement tool without specific device-by-device calibration.